welcome back. In the last lecture, we were discussing about the Schwartz space, and what we wanted to prove is that the proposition if f is in Schwartz space, then f hat is differentiable moreover f hat prime at xi, this is equal to minus 2 pi I x f x hat at xi. That means, what we mean by that, that is, if g of x is equal to minus 2 pi I x f of x, then d by d xi of f hat at xi is equal to g hat at xi. That is what the meaning of this, and then we have seen that it is a question of taking the limit inside. Now, as so what is our in order to show that, what we need to look at is this quotient f hat xi plus h minus of f hat of xi divided by h minus minus 2 pi I x f x hat at xi. Now, this is equal to 1 over h, you can take minus infinity to infinity. This is f of x, and then e to the power minus 2 pi I xi plus h x minus e to the power minus 2 pi I xi x, that is from f hat of xi, and then I can put this as h minus, this is the integral minus infinity to infinity minus 2 pi I x f of x e to the power minus 2 pi I xi x dx the whole mod. This is modulus of minus infinity to infinity f of x, then this is e to the power minus 2 pi I xi plus h x minus e to the power minus 2 pi I xi x divided by h, and then minus e to the plus 2 pi I x e to the power minus 2 pi I xi x dx whole mod. Now, as you can see that because x and f of x, so they are integrable function, they are in Schwartz space, both x f and x f x, they belongs to Schwartz space. For epsilon positive, there exists a n such that integral mod x greater or equal to n mod of f of x dx is less than epsilon, and integral greater or equal to n mod of x f of x dx is less than epsilon. That is the tail of the integral, they are small. So, therefore, what we will do is that we will break this integral into this mod x less than n and mod x greater than n. Now, so this integral, this is lesser equal to mod x lesser equal to n modulus of f of x, and then this quantity plus mod of x greater than n, then this quantity dx. So, that is what we will plug in if we push the mod inside. Now, as what one can see is that in the finite interval case mod x less or equal to n, there will exist a delta such that if, so let us call this as I 1 plus I 2. Now, for mod h less than delta, this I 1, I can find a delta such that this quotient plus e to the 2 pi I x dx. So, this is equal to less than epsilon by n. So, what I am trying to say is e to the power minus 2 pi I j plus h x minus e to the power minus 2 pi I j x divided by h plus 2 pi I x e to the power 2 pi I j x. This is less than epsilon by n. There exists a delta such that this happens. So, this I 1 is less or equal to epsilon by n with the inner one, and then I have got minus n to n mod of f of x dx. If I pull out the supremum of f, then this is what I am going to get, this some constant times epsilon, and in the second integral I 1 is less than, and I 2 being the tail is less than epsilon. Therefore, what you get that the entire thing. So, this is hence we get f hat prime of j, this exists, and this is nothing but 2 pi I x f of x hat at xi. F is in the Schwartz space, then f hat is differentiable. Okay. So, now observe f hat, if f differentiable, f is in Schwartz space, then f is twice differentiable. That is fairly easy. F hat is twice differentiable, that means f hat prime is nothing but, so let g of x is equal to minus 2 pi I x f of x, then clearly g belongs to the Schwartz space, because f is in Schwartz space. Now, f hat prime is equal to f hat prime of j is equal to g hat of j, that is differentiable. Therefore, f hat prime whole prime is equal to g hat prime of j, that is equal to minus 2 pi I x g of x whole Fourier transform at j. Now, this is equal to minus 2 pi I x square f of x j. So, we can continue inductively. So, what we can get as a matter of fact, we will write another proposition. So, if f is in Schwartz space, then f hat mth derivative of xi, this is equal to minus 2 pi I x to the power m f of x whole Fourier transform of xi. So, this is f hat is smooth and f hat derivative can be written as the polynomial times f and its derivative and its Fourier transform. So, this now we can state our theorem, what we are looking for. If f is in Schwartz space, then f hat is also in Schwartz space. So, this is a nice symmetry of Schwartz space vis-a-vis Fourier transform. So, for the proof of this, we have seen f hat belongs to C infinity of R. So, that is the first condition of the Fourier transform is satisfied. Now, what we want to look at is that, so we would like to look at the decay, whether how much of the decay this we can generate, whether this f hat derivatives they are killing the polynomials or not. So, to show the rapid decay, let us look at z to xi to the power n f hat m of xi. Now, look at this. So, this is equal to xi n and this f hat is minus 2 pi I x to the power m f of x whole to the power xi whole hat xi. Now, you take this, let us say call this as the gm, the function gm. In our earlier observation, what you know that this is some constant times g m n and then this hat at xi. I take the nth derivative. Every time you take the derivative of the function and take its Fourier transform, you are going to hit with e to the power 2 pi I xi, and that is why I have put the constant n c here, which will certainly be dependent on n, some constant. More precisely, it will be 1 over minus 2 pi I to the power n. Okay. So, now if I take the modulus of this, then this is less or equal to some constant, and then this is what we have seen mod of g m n at x dx, and this g is a g m is a Schwartz class function, its all its derivative are in Schwartz class function. So, this integral is finite because g m n they have the appropriate decay. So, this is less or equal to some a n m, a constant which is finite. This is true for all xi, hence this is true for all xi, thus f hat this belongs to the Schwartz space. So, it is not just by accident that if f is a Gaussian, then f hat is a Gaussian. The generalization is that even if f has rapid decay and smooth function, then f hat is also going to have rapid decay and smooth function. Okay. In order to do Fourier analysis, so we will be restricting ourselves to do the Fourier analysis on this Schwartz space. So, we can define f hat, and then natural thing is that one would like to ask is that can we have the inversion and the Planck formula for all the function in the Schwartz space. Of course, all these they go to much larger space. For that we would be requiring some more concept about the integrability, and in this course we are not going to deal with this most general theory of the Fourier transforms for integrable function. What we will confine ourselves to develop the analogous theory as what we have seen in for the case of the Fourier series as well as for the finite abelian group in this setting in R, but we restrict ourselves for with to the space of Schwartz space, and certainly this can be generalized. So, but to get a feel for the Fourier analysis on R, to do everything on the Schwartz space is not a bad effort. Okay. So, let us in order to do the inversion or Plancherel, what we have seen is that two things which plays a major role. One is of course the convolution of two functions. So, first let us see that if f and g belongs to the Schwartz space, proposition, then of course, f convolution g is defined. Even we have studied that with the moderate decay how we were able to get f convolution g. So, in this case then f convolution g also belongs to the Schwartz space. So, to see this for Schwartz space, what we need to do is that first we will check that they are infinitely differentiable, and the function as well as all its derivative will have the rapid decay. Okay. So, clearly what we know f convolution g, this is differentiable, and this f convolution g prime of x. So, this we have seen in the circle also, the proof is exactly the same. So, what we can do is equal to, this is limit h goes to 0. I will just sketch it for to recall. So, this is f convolution g of x plus h minus f convolution g of x divided by h. So, this is limit h goes to 0 integral minus infinity to infinity f of x plus h minus of y minus f of x minus of y divided by h into g of y dy, and this is going to be f prime of x minus y, and for the convergence you can take that limit to be break it with the mod x less than n, mod x greater than n, the same argument. So, this will tell that this is minus infinity to infinity f prime of x minus of y g of y dy, which is equal to f prime convolution of g of y. By repeatedly, if we take then f convolution g of k, kth derivative, this exists and this will be nothing but this g, and all this f kth derivative they are again in the Schwartz space. So, we can define the convolution, has no issue over that. So, what we want to show is that x to the power n and f convolution of g mth derivative, this is at x, we want to check the modulus of that. Then this is equal to, I can x n f m convolution of g at x, that is from the above observation. Now, if we take the, so this is going to be minus infinity to infinity x to the power n f m x minus of y, then g of y dy. Now, this is going to be, you look at minus infinity to infinity x to the power n, then this is tau y of f m at x. So, this g of y dy, and this is in the Schwartz space, we get the decay from here, g is integrable, and so we can get that this hence f convolution g also belongs to the Schwartz space. Okay. So, now the next important thing as we are talking about is that presence of a good kernel. So, now recall that what was a good kernel? The good kernel was that if we take a non-negative function, the integral is 1, and away from the origin, if you are taking a sequence, then as n goes, n becomes large, this integral, the area under this family, this becomes very small. Okay. So, to define that, let us say good kernel. We say a family k delta, where delta is positive, delta positive, is a good kernel or approximate identity if 1 k delta of x is greater or equal to 0, 2 integrals minus infinity to infinity k delta of x dx, this is equal to 1 for all delta, and for eta greater than 0, integral mod x greater than eta k delta x dx, this goes to 0 as delta goes to 0. So, this is what is an approximate identity, as we have seen that if you take f a remark, we cannot have, you see the Schwartz space, f convolution g is in Schwartz space. So, like in the Fourier series, we can ask, does there exist a G in the Schwartz space such that f convolution of G is equal to f for all f in the Schwartz space. That is uh, then if this happens, then we say that the Schwartz space has an identity under convolution, but as we know that this cannot happen because of the Riemann-Lebesgue lemma, which will say that if this happens, then f convolution of G hat xi is equal to f hat of xi. Now, I choose my f. So, this is true for all f in the Schwartz space. In particular, take f is equal to e to the power f of x is equal to e to the power minus pi x square. Then what we have got e to the power minus pi xi square g hat of xi, this is equal to e to the power minus pi xi square. Now, we know that e to the power minus pi xi square never vanishes. This will imply that g hat of xi, this is equal to 1 for all xi. Remember that g is a Schwartz class function, therefore, g hat is also going to be a Schwartz class function. Therefore, it cannot be constant, it has a rapid decay. So, this hence conclusion is there is no identity under convolution in Schwartz space. So, once there is no identity, so it is natural to look for an approximate identity. Just like in the series case, we will convince ourselves that why the definition of approximate identity. Thank you.